The following video recording has been made possible by Symbotic, complete warehouse automation. From integrated supply chain consulting to fully automated picking systems with progressive financial models. Symbotic systems are deployed in major grocery, retail, and general merchandise operations throughout North America. Learn more at symbotic.com. And by Duchin Productions, broadcast, corporate, and web video production services specializing in science and technology. Start the conversation today. Visit DuchinProductions.com to learn how video can get your business the customers, talent, and investors you've been looking for.
The title of my talk is Multi-Robotic Coordination with Uncertainty and Limited Communication. So, as we all know, right, multi-robot systems are everywhere now, and they're gonna be even more everywhere in the future, right? And these are a bunch of the examples that we can talk about very briefly, right? Drone delivery, we hear about drone delivery all the time, where there could be a team of these things that needs to go and they pick up packages and deliver them, and they need to think about each other, right? Where the other drones are gonna be in order to try and efficiently pick up and deliver packages. Similarly for UAV surveillance, right? There's a team of UAVs, there's a bunch of surveillance applications that are already in place, both domestic and military settings, where you have a bunch of these UAVs flying around trying to collect information. Autonomous cars, we typically think of them in terms of a single autonomous car, but in reality there's going to be a bunch of different autonomous cars that are out there. They're going to be different manufacturers, so they won't necessarily work well with each other. And there's these other agents out there that are a bit crazy, and they're called humans, and they do crazy things that you don't expect as well. And so autonomous cars are going to need to reason about not only just the other autonomous cars, but also us crazy humans that are still want to get out there on the road and drive our cars, right? As well, there's a bunch of applications in space exploration where you have a team of these things out there. Search and rescue or other disaster response scenarios where we maybe have a team of ground and aerial robots that are working in these environments that are saving people's lives. As well as fault detection, right? So where we could have ground or aerial vehicles that are checking. This is the Sphere satellites on the International Space Station, but you can imagine any of these type of applications for checking pipelines or farms or other type of inspection type applications, right? So I think we can all agree that there's a bunch of these applications that exist now and that are going to exist in the future. But in general, the current approaches for solving a lot of these multi-robot problems are highly engineered, right? They're highly engineered for solving one particular problem or a particular instance of a problem. And they typically specify the behavior of the robot, what each of the different robots in the domain should do, right? They also typically assume either little or no uncertainty. So, for example, we can think about the Amazon Robotics example, and I'm certainly not picking on them, especially since they're a sponsor of this event, so we love them, they're great, right? And obviously the approach works fantastically for what it does, right? But in order to get it to work, you need to set up your warehouse a particular way where you separate the robots from the people, right? And that you have little stickers on the floor so that the robots can localize, and you set up the network so that they can all talk to each other very well. And these ideas, they work very well for this one particular domain, but if you tried to use these ideas for the problems that I was talking about on the previous slide, they wouldn't transfer, right? Out in the real world, there's many other complications that doesn't allow you to engineer the problems to the extent that you can for this particular problem, right? Where you can centralize it and have perfect information about where all the robots are at all times, right? So we're interested in solving more like those problems that I talked about on that previous slide. These more general problems where it's not just solving these one specific things. You're not just solving a navigation problem. You're not just solving a grasping problem. But these problems that may involve doing a bunch of these different activities together with a bunch of these heterogeneous robots operating in concert with each other and thinking about each other, right? And there's a bunch of uncertainty in the real world as well, right? There's sensor uncertainty. Almost every robotics problem has sensor uncertainty, whether it's localization errors or limited sensors or noisy sensors, right? Outcome uncertainty where things happen, whether it's because of the crazy humans or because of limitations of the robots themselves, right, that cause uncertainty. As well as communication limitations. Again, in many real-world situations, we don't have perfect communication with all the robots at all times. So they need to think about these limitations in order to reason about what to do. These limitations and these types of uncertainty are prevalent in all the examples that I talked about before, right? So what we're doing to try and address these issues is we're formalizing the problem, right? So we formalize the problem and the goal. So for instance, in the search and rescue problem, we can formalize it in terms of maybe we have, it's a team of 3 particular ground robots, 2 particular aerial robots with particular sensors and dynamics, and we want to try and rescue the people in the environment as quickly as possible, right? So we can generate a domain specification based on that type of information, and then from that, we want to automatically derive the solutions, right? Controllers for each of the different robots on what they should do at different times based on the information and the noisy communications that they get from each other. So it's often easier to specify the domain, right? We know some information about what problem we're trying to solve and the capabilities of the robots that we have, but we don't necessarily know what the best behavior is. So this is an easier specification to come up with. And then this type of general model makes it so that we can represent any multi-robot coordination problem this way, right? And then we can either optimize or learn solutions for each of the robots based on these type of specifications. So this generality of models makes the problem complex, but we're developing a bunch of different solutions for modeling the problem and solving it based on AI and machine learning methods that we hope will be able to solve these large, interesting problems. So let's talk about a particular example here. We were looking for a logistics domain, and in terms of a logistics domain, the students thought it would be fun, right, in particular, to have logistics in terms of beer delivery rather than delivery of something else. So we have this particular problem here where we have these 3 different rooms where these orders could be made, and we have a bartender here. So here, there's a PR2 here, that's the bartender. There's 2 Turtlebots over there that are the waiters for those 3 different rooms. The PR2 can pick up a drink. It can place a drink inside the cooler that's on top of the Turtlebot. The Turtlebots can get orders. There's a button on them. I don't know how well you can see that, but there's a button on there that can get an order from a person in a room. You can go up to the PR2 to get a drink. And then it can also deliver drinks to the different rooms, right? Where again, the person presses the button to say that they've taken the drink from that particular robot at that point. Right, so the idea now is, so now we can generate a specification for this type of problem, right? We want to try and deliver these drinks as quickly as possible. We have these 3 different rooms. We have these 2 Turtlebots with particular sensors. We have the PR2 as well with the capabilities and sensors of the PR2. How do we optimize the choices, the controllers for each of these robots based on this type of criteria, right? So essentially, for the PR2 case, it's pretty simple. The optimization winds up being that for this case, the resulting controller is that it should pick up drinks as quickly as possible and have them ready for when the PR2 or for when the Turtlebots want them. But for the Turtlebots, it gets a bit more complicated because there's these 3 different rooms. So it needs to try and think about coverage of these different rooms based on the last times that it went to these rooms to visit them, as well as overlap in terms of where the other robots may be at different times, and how busy the PR2 is as well in terms of whether it has drinks available or not. So it becomes a complicated problem to optimize when they should go to the different rooms to check for orders, when they should come to the PR2 to try and get particular drinks, and all those things make it complicated. The resulting policy here, the resulting controllers for these robots, makes it so that there's this complicated dance of deciding when to go to the different rooms based on how much time's elapsed and when they've gone to different places. We compared this as well with an expert solution, which is what we came up with as the best possible solution, and it wound up in the 15 minutes of the experiment delivered 11 drinks versus the 14 that we were able to get from the optimization system here. And the grad students certainly appreciated getting those 3 extra drinks in the 15 minutes. But you can certainly imagine for more, if this is a life-saving situation or an industrial situation, improving the solutions by that much really becomes important at that point, right? So this is a proof of concept domain, but this can be extrapolated to other things, right? And then we can also look at another domain here, a package delivery domain. This one, so this is done in John Howe's ACL lab at MIT. So here we have 4 quads that are going, and as you can tell, it's sped up a bit here. So there's 4 quads that are going, and there's 2 different bases here and here that generate packages. And each of those packages, whether they're there's helicopters, there's goods like health packs and food that need to be delivered there. helicopters here in this airport, and then other vehicles here in this spot over here as well. So the quads have limited sensing range, and in this case are doing onboard sensing for trying to detect what object it is that's generated at the base, and then from that information try and figure out where they should go. So they're trying to figure out which bases to go to try and optimize the amount of these packages that can be delivered over the amount of time. And again, we much improve over the standard methods of trying to do this. And I should also note, so here, there's also uncertainty in terms of, so there's battery life for these particular drones that we have here. So that's what that circle is as well. That gives them information right here. So this is sensing range as well as battery life. So as the battery life goes down, there's uncertainty about how much battery they have left, and they could go to this particular site here to try and recharge the battery. So we have mechanical ways of doing that, but for this particular version, it's easier to just show it here in this way. So, excuse me. So these are particular domains, right? But we can extrapolate this to a bunch of other domains, right? The ones that I was talking about before. And we're working on a bunch of these similar type domains as well that are in terms of doing the surveillance, the search and rescue, and doing in terms of the inspection type problems as well. So, and the number and type of these type of problems is only going to increase over time, right? So in these real world environments, we do need to worry about these types of uncertainty and these types of general problems in order to have these capabilities for having multi-robot systems work in these environments. So we need these new methods to deal with the other robots, the sensors, the humans that are going to be in these environments. And that's the approaches that we're trying to do here is, right, generate these approaches that are able to deal with these type of situations. And I think we've made some good progress, but obviously there's a lot of progress that's still to be made in terms of getting these things to work in a bunch of different applications.